Uh, All right, so PCB. PCB is our process control block. What is that guy? So by the way, if you just wrote process control block, that's not going to cut it. So I could have also asked the question, what is the process control block? So what's the PCB for?
Keeps track of everything.
Okay. Data structure. So basically it's an object, right? It's an object that keeps track of all the crap about a process. Okay, that's crap that the scheduler needs to know. That's stuff that the process needs to know next time it comes around. Next time it's asked, what's the next instruction you're supposed to give? So a data structure for holding process crap. Make sense? So it should have been an easy one, right? So as an effort of embarrassment, how many of you did not get it?
Wasn't there an half or no?
I think I maybe asked what do you need it for? Because we need to know a bunch of stuff about the process. So you could have thrown in things like context switching or something like that. That guy's going to use the PCB for, packing the bags, unpacking the bags, whatever. But at the end of the day, we need a data structure for keeping track of all the process stuff in one place. That would be sufficient. Okay. So, last time we talked about a couple of different queues that the process scheduler keeps track of. So we kind of mentioned 3 of them, right? We have the job queue. Who's in the job queue? What do you mean by running process before I tell you you're right or wrong? Well, you very well might be right. What do you mean by, when you say running process, what do you mean?
Exactly that. I don't know how else to describe it.
Well, describe it more bestest. Describe it more bestest. Most bestest.
The process that is currently being chomped by the.
Okay, so you mean the one that's, when you say running, you mean the one that's currently on the CPU.
Yeah.
All right, that's incorrect. Go ahead.
Job queue is all the processes in the system.
All the processes in the system. So if you had said that a running process is a process that exists, or somebody double-clicked on it, making that process currently in the running, then that would be okay. But saying the guy who's currently on the CPU, not okay. Not okay. So we have one queue that is a collection of all of the processes in the entire system. And how might that guy be implemented? What data structure might we use to represent the job queue?
Right.
Okay, tell me why an array might be a bad idea. Not a wrong answer, but probably a bad idea.
I think it may be stack.
Okay.
So I don't think you can easily add something to an array.
Right, arrays are fixed size, right? So arrays are fixed size, so we'd have to make some sort of best guess at what the maximum number of processes could be on a machine, right? And then beyond that, we'd say, okay, I'm going to create gigantic mansion to hold all the processes that could ever possibly exist in this machine, of which we at any point in time have 3 guests staying in the mansion, for example. Okay, probably not real memory efficient. Okay, why would a stack be a bad idea? Okay, well, stack is really maybe too specific, right? So we need to think about what's the job of that job, pun intended, I guess. What's the job of the job queue? We're just holding a collection of all the jobs that are currently in existence, all the processes that are currently in existence. Are we needing to organize them in an interesting way where we're pushing onto the top and we're popping off the top? We just need to hold them, right? What's our generic data structure for holding arbitrary size data sets? Yeah, linked list. So stacks are like linked lists, but we don't need that special aspect of it. Now, having said that, let's go a step further. Would you implement this using a generic linked list? Or might you implement a job queue using a queue? Heap is going to make much more sense for the running queue. The queue dealing with the ready queue, the guys getting ready to get onto the CPU. Yeah, because that might be, priority might be important. So if we're just holding a collection of stuff, now think back to your CSC300 days when we wrote linked lists and then we wrote stacks and we wrote queues. Remember after we wrote the complex general purpose linked list, remember how easy stacks and queues were? Add front, remove front for stacks, called it push and pop. And then add end, remove front for NQ and DQ. DQ, soft serve coffee. Christian worldview.
Where?
I made you think about it right there.
Just the word.
Done. Nailed it. He was baptized in Diet Mountain Dew yesterday. 2 days ago. True story. Okay, so in any case, we probably use a queue because we don't need a full-fledged general purpose linked list for keeping track of our job queue. We just need to put stuff in and take stuff out, right? Things will be leaving the job queue and then going into into something else. Okay, so I want to kind of think about that a little bit.
Your slide puts it even worse than you did.
Who?
The slide.
This one?
Child, and then the child executes something.
Oh yeah. Well, sometimes you procreate bad eggs. So yeah, I mean that's the way it works. Because his time slice has expired. He had execution coming. All right. So what's up?
The Hitler Jungen. Hitler child.
All right. So let's. Do I have a plain Jane picture? All right. This is my picture with some dinosaurs on it. All right. So we have our job queue. Job queue. Boom. All right, and this guy might look like this. And we're going to give these guys we're going to give these guys incredibly unique process IDs. What's the process ID again? Okay. So we can tell processes uniquely apart, right? Kind of like our social security numbers or our telephone numbers, whatever, that kind of stuff. Our student ID numbers. All right, so here's all the current PCBs that are in our job queue. So PCB is a wrapper for a process, right? It keeps track of all the crap, all the information about an individual process. All right, now we have another kind of queue. And let's see, does the book call it ready queue? Yeah, they call it the ready queue. Okay, so now we have a ready queue. All right, and the ready queue, let's say, is going to have, currently it's going to have these two guys in it. All right, so these two guys point to the exact same place. All right, so they're in the ready queue, and the last one was called what? The barbecue?
Device queue.
Get it? Get it? Barbecue? Love barbecue. Did you guys see on Facebook the barbecue I had this past weekend? It was I was in the middle of nowhere, Wisconsin, Toma, Wisconsin, and there's this guy who is been on barbecue pitmasters and does all these competitions and won like grand champion stuff, and he had a catering business there in the middle of nowhere, and that he uses to fund his travels for these barbecue competitions. Well, he just opened this little shack for barbecue. Top 3 things I've ever put in my mouth. It was just completely epic. That is a euphemism. All right, Christian worldview. So it was pretty legit, like to the point where it's worth a 3-hour drive out there for lunch. It was that good.
Where do you want to go for lunch?
Toma, Wisconsin.
That is the middle of nowhere, trust me.
What's it called?
The place was called, was it BD's Barbecue? It was this new restaurant. Yeah, it was. I mean, and it was a small place, but it was kind of nice inside and stuff like that. It was. So I have a picture on Facebook. You can go and read about him and stuff like that. But I took a picture of him back by his barbecue pit. So.
BD's like BD's Mongolian barbecue or like
No, it's 2 words. B and then I think it was BD. So let's check. But Punchline is very, very, very legit. Maybe it's JD's. I might be butchering the BD's thing.
It's BP's.
BP's? All right. Yep. BP Smokehouse Barbecue. Yeah, so the B is the guy's wife's name. The guy's name is Darren Price. It was very, very legit. So if you ever have any sort of reason to head to it's about an hour and a half north of Madison, maybe about 40 minutes from the Dells. If you're at the Dells, totally worth a ride. All right. So we have our barbecue. So we have our device queue. And what's the purpose of the device queue? So these guys are the ones ready to get chomped by Pacman, right? Okay, these guys say, okay, I'm ready to get my CPU time. What's the people in the device queue? What are they there for?
Waiting for I/O.
Waiting for something, probably I/O, right? All right, so let's put 4 and 5 down there. All right, so these guys are waiting for some I/O, among other things. So they're waiting for access to some device. Hard drive, the network interface card, whatever. Some device on the system to get something from it. All right, so we have 2, so who's not in here? 1, 3, 7, and 8. Okay, so several of these jobs are currently not in any of these queues, which means that they're probably either new or about to be terminated. One of the two, right? So these guys haven't been scheduled yet. So we have a dude that sits in the middle here. It's actually kind of sort of 2 dudes, but we have the scheduler. And the scheduler's job is for maintaining these queues. So we have one person who schedules for these queues, and then we have a second scheduler. Some systems it's just one, but we have a second scheduler who actually manages. Gotta get a Pacman picture, of course. Boom. Oh, perfect Pacman, right? Nope, better Pacman. Boom. All right, so there's our CPU. So we're going to call this guy the CPU scheduler. And we're going to call this guy, for lack of a better word right now, let's call him the queue scheduler or the process scheduler. I think your book probably calls it the process scheduler. All right, so this is the process scheduler who's in charge of moving things in and out of the job queue into one of these other queues. Okay, and then he works hand in hand with the CPU scheduler who actually is in charge of taming the beast. So he feeds Pacman. This is our CPU, by the way. Can I write on this?
That's what I thought too.
You thought what?
He was gonna animate it.
That would have been awesome. Abba. Now I have to record my own track. All right, so In any case, this is our CPU over here. So just in case any of you actually think Pacman lives inside of your computer, he does, but for a different reason. All right, so CPU scheduler feeds the CPU with PCBs that are currently in the ready queue. All right. This dude is in charge of marshaling jobs from the job queue into one of the other queues.
So what is Pacman eating? PCBs?
PCBs.
Those little dots?
Little dots. Well, it's actually, a PCB holds a bunch of information about a process. So what does Pacman actually eat? Magic tricks. Okay, so inside of the data section of a PCB, we're going to have a list of all those magic tricks. Okay, so we need to, those get squeezed out. All right, and that's what he's actually eating. He's eating magic trick 1, 2, and 3 from this PCB in this case. Go ahead.
So are magic tricks synonymous with processes, or are they?
A process is a process is generated when let's just say a high level, let's say you write your Java program or your C# program, and then you compile it. It compiles down to a big list of instructions, assembly language instructions, which I refer to as magic tricks, that the CPU knows how to do. Remember we talk about low-level languages have a one-to-one relationship with the CPU? Every line of code in a low-level language translates into exactly one magic trick that the CPU knows how to do. So this PCB, this object here, holds a whole bunch of stuff. He holds the program counter, he holds the current state of the registers, and then somewhere in there he has a data section that has all of the magic tricks that he says, I need to accomplish this magic trick, then this magic trick, then this magic trick, and then my job has been done. All right, so what we actually do is the PCB reaches into his pocket and throws the next magic trick, the one associated with, well, actually it's the CPU scheduler who does that, but throws the next magic trick, the one that's associated with the program counter in the PCB at Pacman so that Pacman is happy, I guess. Because Pacman's job is to stay busy 100% of the time. He constantly eats. Right? This is actually kind of interesting, as much as Pacman eats, that his shape stays so consistent.
Rather slimming.
Well, it's not, I wouldn't necessarily say slimming, just consistent.
No, it's a little.
I mean, a skinny Pacman would not look right.
It's pretty
Well,
flat.
can I-
I mean, I'm just saying.
No, well, I guess whatever.
It's in 2D after all.
That's true. Although there's some shadowing going on here. I believe this is a curve. All right.
Perfect good.
Yep. All right. Yep. So yeah, these guys are actually magic tricks that come from the data section of a PCB. Make sense? All right. So that's what's going on there. So this is kind of a picture of our what's happening inside of the process and the CPU schedule. We'll talk about this part specifically. Right now, we're kind of sort of talking about this part. So at this point, we're not really talking about how this happens here. We're just talking about how things get from the job queue into one of these queues, and we know that Pacman feeds off of the ready queue somehow. Okay? So let's go here. Well, they call it long-term and short-term scheduler, whatever. Okay, so long-term scheduler, this is the job scheduler, selects which processes should be brought into which queues. So this guy would be called the, by your book, long-term scheduler. And this guy would be called the short-term scheduler. All right, so short-term scheduler only operates off this one queue and says, okay, in real time, as the CPU needs to stay busy, I need to decide what's the next instruction he gets. And that's going to fall into the category of which PCB does it come from, and how do I get that instruction to Pacman. All right, so short-term scheduler selects which process should be executed next and allocates the CPU and then starts feeding. And they mentioned here sometimes there's only one scheduler in the system. I think I said that a few minutes ago, but what does that even mean? I mean, basically what they're saying is you might have this monster over here called the scheduler, and the scheduler, let's send this guy to the back. Send to back. And this scheduler is an object that has two threads in it. Each one of those guys does the 2 different scheduling thingies. So this would be an operating system with 1 scheduler that happens to do 2 separate things. It's 2 schedulers. Make sense? So I like this original picture better. Okay. So that short-term scheduler, it's invoked very, very, very often. So this guy's going to be very busy because our CPU is really, 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 really fast. And again, we have this job inside of our operating systems where we're trying to fake out the end user, make the end user feel like all their stuff is happening at the same exact time, right? So this short-term scheduler, the guy who's in charge of feeding Pacman, he's going to have to make the decision, does the next magic trick come from the current PCB, or do I execute a context switch? What's a context switch? All right, so the current PCB packs his bags, that is, copies over the current state of the CPU so we can leave the CPU, and then the new PCB kind of steps into position and he unpacks his bags onto the CPU, loading the registers to their last known state for him so that he can eat the next magic trick without too much indigestion. All right, so long-term scheduler is invoked very infrequently, seconds or minutes. This guy is less, I guess, less demanding because he's sitting up here and he's moving things from the generic job queue into our ready queue. Okay, so he's in charge of moving things from this queue into the ready queue. And all he has to do is make sure this line stays filled up. Right? Okay. This guy might do some ordering changes, or this guy might do it as well, but when he adds somebody to this line, he might add him to the back, he might add him to the front, he might add him wherever, to the middle. So this guy's going to be ultimately in charge of getting people into this line. This guy's in charge of feeding Pacman from what's in this line. So as long as there's at least one process in this line, assuming there's any processes in the system currently vying for CPU time, which because of the operating system itself, there would always be at least one process in there. This guy's going to have to be less busy because he only needs to put things into the ready queue that need to go into the ready queue. Okay, he's not just going to drag people out of line and throw them into the queue and say, okay, you're getting CPU time whether you need it or not. Let's see. So, a long-term scheduler controls the degree of multi-programming. So again, if we kind of extrapolate forward and think about what if we have 2 Pacmans. So what do we have here? We have here's our dual-core computer. It's a mating pair, by the way.
They don't have wastes. How do they?
You don't know how Pacmans reproduce?
Do they just kill each other?
We create this.
About these CPU packers.
We create this gigantic backstory on the mating rituals of the fictitious Pacman representation of our CPUs.
Magic tricks are actually little Pac-Mans without mouths or eyes.
So he's actually eating their young. All right. So in any case, we have multiple CPUs here. Therefore, do each of these CPUs have their own ready queue? Let's think about this from an operating system designer perspective. Does each CPU get their own ready queue? Go ahead.
No.
All right. So you think there's one big ready queue for all the CPUs?
I would tend to think that because you don't know what processor somebody's going to have in the system. You could have a single core, dual core, quad core.
Okay.
So you're trying to design an OS for all of those.
All right. So part of it has to do with designing a generic OS that is malleable for the type of hardware it's running on. Okay. Something else. If the long-term scheduler, our process scheduler here, if he's throwing things into various ready queues, how does he decide which ready queue to put things into? Well, it's a little bit different problem than we might think of in real life. So let's just, for the sake of argument here, create a second ready queue. Wow, I literally just achieved the impossible. All right. So he's going to create a second ready queue, and let's say these guys currently have 7 and 8 in it. All right, so in real life, the process scheduler is the, I mean, this is eventually going to happen, right? We already have greeters at Walmart. We're going to have greeters at McDonald's. So you're going to walk into McDonald's, and the greeter is going to point you to the line they'd like you to enter, right? So the human version of fairness, if we have 2 registers open at McDonald's, the human version of fairness is let's get in the shortest line, right? Shortest line is likely, I mean, obviously you probably take some other things into consideration, but shortest line is likely the line that's going to move the quickest. Okay, just keeping it simple. Does that necessarily work in a multi-programming type of operating system? We've already talked about the possibility of a single program having more than one process representing it, right? So even though we've also talked about the benefit of threads in terms of not taking over the operating system, a thread isn't always the solution. Sometimes you need a heavyweight process for maybe, let's take a complex piece of software like Photoshop where it might be doing 2 or 3 kind of large tasks that really belong to their own application, right? So different, almost like the armed forces or something like that. They all are solving a similar problem, but they all work independently. All right, so, Photoshop might have a compression engine, and that's running in its own process. And it might have another engine that handles the actual GUI for Photoshop. Let's just take those 2 as an example. And each one of those might have their own threads inside of them for handling things that are specific, multi-programming things specific to that one process. Okay? And remember, threads are managed by the process itself, so they don't get more CPU time. Now, so it's possible we have one process that belongs to Photoshop here, and we have another process that belongs to Photoshop here. And these guys are in separate lines at McDonald's. All right? Now it could be that, let's say it's 2 and 8. So 2 is one of the Photoshop processes, 8 is another Photoshop process. Well, let's say that 2 is next in line here, but he can't actually do his job until 8 has done some of his job. They might be reliant on each other. Okay, that's typically not the case in a McDonald's. When the greeter puts you into a different line, they're putting you into the line that's the shortest because they assume that you're self-sufficient. Okay, but what wouldn't make sense at a McDonald's is if you walked in and it was a dad and 2 kids. If the greeter put the dad in one line and the 2 3-year-olds in the other line. Chances are they're not going to do a real great job of ordering themselves. And even if they do, paying is going to be a problem. All right? So they're going to require dad bring the money over to the other register. Make sense? Okay, so those become, that's a scheduling conflict. So in our operating systems, those types of situations may arise very often. Therefore, we need to take that into consideration. All right? So maybe we have a single queue that everybody gets into. The short-term scheduler then decides who actually gets CPU time next, and more specifically, which CPU do they have which CPU are they going to get? Okay. Yes, we have 2 CPUs, but what we should think about is these guys as being generic resources. We have 2 resources that this guy is in charge of managing, and he's going to pay attention to the ready queue and say, okay, well, you're next in line for whatever reason. We haven't even started talking about prioritizing these guys, but you're next in line for whatever reason. Let's find out who you are, what you're doing here, what resources I have available, and assuming I have more than one, which one is most appropriate for you. Does that make sense? So this guy's job becomes very complex, especially as our hardware becomes more and more complex and our operating systems become more and more capable. Make sense? Okay, so the second we start adding more CPUs, and now let's add 4 CPUs or 6 CPUs or 12 CPUs, whatever it is. And then each of these CPUs, if we talk about, the hyper-threading thing, So these guys are farting stars.
Children before they grow up.
Right. Okay, so these are two hyper-threading CPUs, and the hyper-threading CPU, kind of acts like it's a dual-core CPU in and of itself. All right. Well, if this guy is a dual-core, now each of those cores has their own 2 stars, so it's almost like a quad-core CPU. So a lot of times they'll advertise it as how many cores and then how many logical cores. So we'll talk about hyper-threading at some point. If not in here, we'll talk about in the architecture course. Relatively unimportant for a operating system world because it means the same thing to us, mostly the same thing to us, as just having multiple CPUs from a operating system design perspective. Okay, so in any case, this guy's job becomes more and more complex as our operating systems become more and more capable. Okay, and our hardware becomes more and more capable. This guy just needs to keep this line filled with something. Make sure that there's something, if there's anybody on the computer that needs to have some CPU time, make sure he's in that line somewhere. Okay? About half of my last minute was being dictated there. Somewhere in there it thought I said, "Hey Siri." Except it didn't think I said it there.
Hey Siri, what are you doing?
I'm surprised people aren't getting hacked that way. You run up to somebody and just yell, "Hey Siri, call mom," or something like that.
You can turn off access from it.
Yeah, but you might not. But you might not.
Yeah, there we go.
Yeah.
It's like the Xbox One.
The bigger question here is I keep saying it.
Yes.
Yeah, you're fighting with your friends over. The funny thing is that I think I have Hey Siri turned on. Hey Siri, call mom.
What is your mother's name?
You'll never know.
Huh?
Two persons here.
Two.
The NSA won't know, Siri.
When I got my first, the first iPhone that had Siri in it, my wife played a joke on me, and it was pretty funny. So you know how Siri is supposed to kind of learn about some of your mannerisms and stuff like that. This is day 2 of it, so not very experienced using Siri yet. I pick up, how those of you who've gotten used to using Siri, maybe you can tell Siri what you'd like Siri to call you, right? How you want Siri to refer to you. So I pick up my phone and I'm using Siri or something like that, and Siri says, "Okay, fatty." It's like, are you serious? She's getting a little mouthy.
I can tell you off recording what you told me one time.
All right, so
Me?
more into our schedulers here. So short-term scheduler, we already talked about that. Degree of multi-programming, that's why we were talking about the number of CPUs. Now when we say this guy controls the degree of multi-programming, as we've advertised here of having a single queue, if this guy controls the degree of multi-programming, how does he control the degree of multi-programming with a single queue? Or how might he control the degree of multi-programming from a single queue? What does multi-programming mean? Okay, that's multi-processor.
Isn't that the computer's way of multitasking?
Certainly related. So multi-programming would be the capability of a computer to run more than one program at once. So certainly related to multitasking. If the process scheduler is in charge of the degree of multi-programming, what does that mean? What does it mean to control the degree of multi-programming? What is the degree of multi-programming? How many programs you can run at once, right? And they're saying the long-term scheduler is in charge of that. How does one control how many programs can run at once?
programs that are running and don't allow any new ones to be created.
Okay. Well, all this guy knows about, though, is these queues. He's not in charge of the resources themselves. Plus, this one's slow. This is the McDonald's greeter. This is the fry guy.
Can you see how fast the queue is being run? Like the time which it takes for processes to be
Well, let's think about the chicken or the egg problem here. We've said that this guy needs to be fast, right? He's getting called very, very, very often, and our job is to keep the CPUs as busy as possible. So whatever task he's doing, it needs to be fast. So is it in his best interest to talk to the next PCB in line and say, oh, should you go to this CPU or should you go to this CPU, depending on what's currently on the CPUs? He's asking a whole bunch of questions now, right? Is it in his best interest, or is it in our best interest, I guess, from a consumer using the operating system perspective? Is it in our best interest for this guy to do that extra thinking? Or do we want him to do the minimal amount of thinking possible to accomplish his exact task, and that is to feed Pacman? Feed Pacman. So, if this guy's in charge of the level of multi-programming, wouldn't that indicate that we actually have more than one queue? A queue per resource? And then this guy feeds off those queues? Now, having said that, is this queue specifically for this processor? And is this queue specifically for this processor? And here, let's throw 7 and 8 in there. Before we had PCBs cheating, getting a little double time, but I guess running at the same time, which might be problematic. We'll talk about race conditions. They're bad. All right. So, is everything in this ready queue earmarked to go to this processor and everything in this ready queue earmarked to go to this processor? Or can any of these PCBs go on any of these processors and this guy just dictates when a processor becomes available, who's next in line? Probably the second one kind of makes some sense, right? Okay, so this guy's the bouncer allowing somebody into the bar. These are the two different bartenders. Okay. Very appropriate for a dry campus, Christian worldview. All right. So, in any case, the bouncer lets them in, but needs to send them to the correct bartender depending on who's less busy, right? Okay. So this guy needs to decide. But now it's not just about who's less busy. If we have two people in the front of the line here, we have to decide who gets to go next. We have one open process. All right, so we'll keep going with our bar example. All right, so you're the bouncer at the door. There's two separate lines at this weird bar. It's the only bars that would have two lines. You'd have like the VIP line, so you'd always feed off the VIP line, right? But we have two equal lines for no good reason other than just to match my example here. All right, so the bouncer has to stand there and he has to decide. Actually, I ran into this problem the other day. We're going to use a real life example. When I picked up the new iPhone at the Apple Store, they had two lines that seemed to have equivalent priority. You had the people like me who had pre-ordered their phone and set an appointment for a very specific time. And then you had people who, to pick up in the store. And then you had people in the other line who just randomly showed up and were handed a time. So one would think that I would have been in the VIP line, right? And that the steerage were in the we'll get to you when we can get to you line. Totally not the case. We had a bouncer who dictated who the front of each line who was going to get to go next. Me, who made my appointment weeks ago, or the person that on a whim showed up this morning. All right, so That's our scenario. Two separate lines of equal priority. One bouncer, one gatekeeper to our CPUs. Who gets next? So now this CPU just became available. Who gets that CPU and why? How do you make the decision?
Which one would be fast?
Is that, I mean, that's not necessarily wrong. Is that a legitimate measure? Let's solve the problem in real life first. Okay, so I'm the bouncer at the Apple store, in which case I would have certainly let myself go first, right? And the other thing, they actually implemented our line as a heap. They allowed people to cut in front of us. Like if somebody was like 10 minutes late for their slot, and they would let them go in front of us, even though we got there on time for our slot. So I didn't get in until 9:20 when my appointment was at 9, when people who were supposed to be there at 8:30 showed up at 9:10. And they got in before me. Terrible. All right, so in any case, the human fairness is going to say what? We have two lines. We might choose to look at which line is longer. So we might say, well, I want to keep these lines of relatively equal length. So whichever line is longer, we're going to feed off that one because that must be the one that that hasn't gotten CPU time as recently, something like that. Okay, one possibility. But we're at the mercy of our long-term scheduler over here. What line has he put the last dude into? And why did he put him in that line? We don't know. All right, that's our greeter. The greeter just said, okay, we have a line with 2 people in it. We have a line with 40 people in it. Why don't you get in the 40-person line? Well, why? Look, I'm on pills and I'm senile. All right, you get in the 40-person line now. All right, so there might not be a rhyme or reason, but the important thing here is that this dude doesn't know what this dude is doing and why they're doing it. Okay, because this person is in charge of the level of multi-programming. He chooses which line they get into. Okay, so there might be a very specific reason that some PCBs are in this line and other PCBs are in this line. Make sense? All right, so now this guy, remember, one of our goals for this guy is he needs to be fast. His level of decision making has to be minimal. It has to be accurate, but it has to be minimal. Go ahead.
Just switch between 2 lines.
Okay. Could.
It wouldn't do much for any a difference in length between the lines, but it would be quicker.
Okay. So you might just have a toggle switch essentially, right? Okay. CPU's open. I let this guy go. This line was the last one served, so now you're going. Go ahead. CPU's open, go ahead. CPU's open, go ahead. CPU's open, go ahead. No harm, no foul, right? Okay. Certainly would be fast.
What about scheduling conflicts?
Okay. Well, what does a scheduling conflict mean?
If one is dependent on the other permission first.
Hold that question for next time. Who's in charge of that? It's going to be this guy right here. All right, homework assignment. Write your take on a Java implementation of a simple PCB. So first of all, you have to understand the question I asked. Understand that PCBs are data structures. Think about the things, the simplified number of things we've said we need to store in that data structure. Now go and create a PCB data structure. Make sense? Well, you have to figure it out. I'm asking you to create a data structure in terms of our PCBs that we've talked about. And here, I'll leave it on an interesting screen that might help.
So is it
Yeah, that one would be a decent one.
Okay, is it going to be a little 14 chunk?
So just look at the very end of the class video, and you'll see this slide that gives a C representation of what a PCB might look like. I'm asking you to write a Java implementation of this. Okay? And that's due next class.
We have to create PCB too, like the actual like data structure for that.
I want you to rate the PCB. That's what I'm asking you to do, is rate the PCB.
Oh.
For the 390 homework, you know how you